Good morning, everyone. I'm Sumit. I'm a marketing professional working with Oxford University Press. I hope all of you are taking good care of yourself. Uh, we welcome you all to this webinar, and which is a collaborative effort between Shama Prasad Mukherjee College for Women and Oxford University Press India. Thank you, Rima ma'am, for coordinating with us for conducting this webinar, this session, and of course, thank you, Dr. Sridhar, for agreeing to conduct this session. So, before participants move forward, a brief introduction of Dr. Sridhar, and then over to you, sir.
Thank you.
Dr. S. Sridhar is Professor, Department of Information Science and Technology, College of Engineering, Guindy Campus, Anna University, Chennai. He has more than 20 years of active teaching and research experience, including a brief stint at National Institute of Technology, Trichy. Uh, a PhD from Anna University, he has specialized in medical imaging and has published several papers on the subject. And of course, he has authored 2 books with Oxford University Press India, Design and Analysis of Algorithms, the one you can see on the screen, and the other one is Digital Image Processing. Sir, can we start?
Yes, sir. We can
Yes,
start.
sir. Thank you, sir.
Good morning to all of you. I am very happy to be part of this webinar. I am asked to take 2 topics, approximation algorithms and randomized algorithms as part of this session. So today, this is going to be my agenda. So what I'm going to do is that I'm going to introduce you the concept of approximation algorithms, and I'm going to talk about randomized algorithms as part of this session. So my session will highlight some of the design strategies that are available for us to design programs as part of approximation and randomization algorithm. And we will also be introducing various problems that are coming under this particular category. Um, Before we start the topic of approximation and randomization algorithms, we have to understand the context of these algorithms, right? So we will start with the word complexity. So what is meant by complexity? Complexity means the difficulty that is involved in solving the problems. So you have 2 categories of complexity. One is called the computational algorithmic complexity, and another is the computational complexity. So in if you take computational algorithmic complexity, so we will have different types of algorithms like polynomial algorithms or exponential category algorithms, which are called non-polynomial deterministic algorithms. Computational complexity is different from algorithmic complexity in the sense that this deals with the problem as it is. So given a problem, can we able to solve the problem or not? So based on that, we can categorize the problems as easy problems and hard problems. So all of you might have aware of algorithms like linear search, sorting algorithms. So you might have solved a number of problems in a dynamic, greedy approach, etc., etc. All these algorithms are coming under easy problems because the complexity analysis of those algorithms are polynomials. For example, if you take the computational complexity of a merge search, it is order of n log n, which is nothing but a polynomial. Polynomial problems are very easy problems to solve because they take only a finite computer resources such as memory and CPU time in order to get executed. Maybe you have to perhaps spend few minutes or hours actually to solve these sort of problems. But there are other category of problems which are called hard problems. Hard problems means these problems are very difficult to solve, and it requires exponential polynomial algorithms for that. For example, if you take algorithms like traveling salesperson problem, the computational complexity is of the order of 2 power n. So that means if you try to increase the number of n's actually, the amount of time to execute these algorithms are very large, and some algorithm may take many days or even months together to do that. So these hard problems can be categorized into two different categories. One is called the NP hard problems, and another is called NP complete problems. NP hard problems are mostly intractable problems. For example, if you take some problems like what you say, the Fermat last theorem, or if you take the halting problem, etc., etc. So people have given the proof that these sort of problems can't be solvable at all. So in other words, we don't much say to these sort of problems which are proven to be intractable in nature. But on the other hand, there are certain category of problems called NP complete problems, where these problems are very hard, but the property is that if we solve one problem, then all other problems will be solved. For example, traveling salesperson problem is a very difficult problem to solve. Hamiltonian problem is also very difficult problem to solve. And traveling salesperson and Hamiltonian is related in such a manner that if one fellow smartly solve TSP problem, automatically the Hamiltonian problem will get solved. These sort of problems are called the NP complete problems, where these problems will be solved theoretically, but requires lots of computer resources for that. The person who is shown in this particular figure is Stephen Cook. He researched a lot in this particular category, and he has given a method for giving a proof for NP complete sorts of problems. The background of our talk is going to be this category only, where we are having difficult problems to solve. So if you take the real world problems actually, you will find that only very few percentage of the problems are solvable in nature. The majority category of problems are either intractable problems or NP complete sorts of problems. For example, you take problems like weather forecasting. Weather forecasting is a very tough problem, which can be called as a N-body problem, which comes under the category of NP complete sorts of problems. So in real world, most of the problems are what is a very difficult problems only. How do we write programs for this? We can't escape from the fact by saying that these problems are very hard to solve. So we have to give some sort of a solution. So we require some sort of a methodology, and in this context only, these two strategies are coming into picture. That is the approximation algorithm and randomized algorithms. That is the context now. So today, what we are going to do is that we are going to discuss some difficult problems if the instance is very large, and for those problems we are supposed to make a solution means how do we approach these sort of problems. Okay, so this is where the approximation algorithm is coming into picture. So you know very well. Suppose if somebody is asking to tell a number 2.1313131313. So what I do? So instead of repeating that, I try to approximate saying that the number is 2.13. In other words, I can't express the original thing. So we do some sort of an approximation. In the same manner, the problem that is given to me is very tough, so I can't apply the exact algorithms. because either it is impossible or because I don't have sufficient resources to solve these sort of problems. So in this case only, we are going for approximation algorithm. So in approximation algorithms, we are trying to get not exact optimal solutions, but we are simply satisfied with the near optimal solutions. So we are aiming to produce some closer results, which is more than sufficient because something is better than nothing. Therefore, we are opting for this sort of things. So, in other words, the idea of approximation algorithm is to get solutions for some problems which are otherwise very difficult to do. Fine. What is the trick we are going to do to solve this sort of problem? Because we have already said that these problems are very difficult to solve. Fine. Original problem may be very difficult to solve, but we can make some compromises by relaxing some of the constraints. So you know very well, we are dealing with optimization problems. In optimization problems, normally we will have an objective function and then we will have some sort of a constraint. Say for example, now I am addressing you for a lecture. If a friend of mine wants to meet me, I can give time for him because the time will overlap with my lecture time. So this is what we say constraint. So this is a difficult problem because the constraints are contradicting to each other. So the question is, whenever the conditions are contradictory, the problem becomes unsolvable. For example, I can't address you, at the same time I can't chat with my friend. So the possibility is I may have to relax certain considerations. Maybe perhaps I can say to him saying that fine, after 6 I am free to meet him. So by relaxing some of the conditions, suddenly what happens is that the problem becomes solvable in nature. So what we are trying to do is that we relax some of the conditions and then we are trying to transform that problem into another problem of an easy instance, and then we try to address that problem using some of the known strategies and we try to solve it. After solving that, then we try to see whether the original constraint can be brought back into the problem. So if it is possible means then possibly we will try to find some sort of a near optimal solution for that. So the strategy is very simple. So take a problem, difficult problem, understand the constraints, relax some of the constraints, and with that simplified problem, you try to find the solution for that. And after finding the solution, reimpose the constraint and see whether the solutions can be altered or can be used as it is for the grand instance. So this is how we are going to deal with that. So what is the kind of strategies we are going to follow? Means heuristics we are going to follow. We are going to follow some sort of a greedy programming for these sort of problems, and we are going to use linear programming techniques to solve these sort of difficult problems, and then the dynamic programming we are going to use for these sort of problems, right? Fine. Before going into that, we will introduce one important concept called what is a approximation or epsilon or the approximation ratio for this problem. Because approximation algorithm comes with a proof and performance guarantee. So I have to say, fine, this is a difficult problem. So I am going to convert that into easy problem and I am going to solve this, and I have to give performance guarantees. And that performance guarantee is what we are going to see as part of that. In other words, approximation algorithm are not just what is it, some trash solutions, but instead these solutions have got some strong fundamentals as well as guarantees that come along with these sort of problems. Fine, you take this particular problem. So let us assume that this is a traveling salesperson problem. So I am going to start from node A and I am going to go to B, I am going to C, D, and then I have to come back. For example, if I go randomly like this, for example, A to B, B to C, C to D, and then D to A, I'm not following any logic at all. I'm simply following some sort of a random walk. If I go like this, what will happen? It is 1 plus 2 plus 1 plus 6. Therefore, it is going to be 10. So this is some approximate solution I'm getting. But actually, what is the actual solution? Means actual solution is A to B, from B to D, D to C, and C to A is going to be the actual one. And what is the value of that? The value of that is going to be 8. So that means the ratio of the approximate solution and the original solution is 1.25. So in other words, how I will mathematically present my algorithm is that my approximation algorithm is random walk, but what is the margin of error? The margin of error is going to be 1.25 epsilon. So this is the performance guarantee we have. In other words, all the algorithm which comes with some sort of a bound of epsilon is called what you say the approximation algorithms, right? So I am going to start with one difficult problem that's called a traveling salesperson problem. This is a very classical problem. All of you know very well. So if there are 5 cities, I will start from one city. I have to visit all other cities only once, and I have to get back to my original city. So the question is how to find the shortest route that enables me to visit all other cities only once, and I'm coming back to my original city. This is the traveling salesperson problem. What is the issue in that? Means for some smaller instances, for example, 5 cities, 10 cities, 20 cities, the algorithm will really work. I can give you the algorithm, I can give you the complexity, and I can give you some sort of a numerical problem also. So for smaller instances, there is no issue at all. When this problem becomes very difficult, this problem becomes very difficult when you have a large number of cities. For example, let us say if you have some 1500 cities, means complexity is 2 power n, suddenly it becomes 2 power 1500 approximately. And even if you assume that going to one city takes 1 minute, actually, suddenly we have years actually. This is the issue. If that is the case, if I take a United States and if I connect all the cities together by means of a route, and if I have to, what you say, define a traveling salesperson problem means suddenly things becomes very difficult. And you know very well every year there are being contests being held to give some efficient solution for what is a TSP. So even now, we don't have any successful solutions for these sort of problems. All are research problems. We find it very difficult to solve these sort of issues actually. So the question is, fine, this is a very difficult problem, but for my company, I have to use this sort of solutions. For me means what will I do? So that is what I will try to see as part of this. So I will try to define an approximation algorithm with some constant approximation ratio. So that means I have to find some epsilon and I have to define some sort of a method for that. Fine. First design strategy I will try to do is that I will try to find some sort of a heuristics. So what is meant by heuristics? Heuristics means these are some educated guess, or we can say some sort of a common sense solutions, or we can say this is some sort of a thumb of rule actually. So the question is, for a given problem, we can find some sort of a heuristic, and then we will try to apply to the problem actually, and then we will try to get some sort of a solution. As I said earlier, this is not the exact solution, but this is a approximate solutions I can have for my particular. So what I'm going to do, I'm going to TSP problem. You know very well it is nothing but a undirected graph. So what I'm going to do is that I'm going to convert that into some sort of a minimum spanning tree. You know very well what is a minimum spanning tree. So minimum spanning tree is nothing but a tree structure of a graph where all vertices are present, but the connectedness will be removed. In other words, there is no cycle in your what is a minimum spanning tree. So what you will do is you are asking me to find the solution for a very difficult problem called a TSP. So what I will try to do is that I will try to find a transformation of the problem to a simple problem of a MST, and then I will try to find what you say the path. So, what about the restriction that only one city should be visited at a time? So, for that, what I will try to do is that I will try to reinforce this constraint at the later on stage, and then I will try to modify my solutions. So, my strategy is going to be something like I'm going to find a minimum spanning tree, and I'm going to start from a root, and then I'm going to do some sort of a pre-order tree walk, and then I will try to do the restrictions. So these are the various cities I have. So what I'm going to do is that I'm going to find MST. So now you see this is a MST. Why this is MST? Because you can find that there are no cycles in this particular thing. For example, there is no cycle here. So whenever I remove the cycle forming edges, I get some sort of a MST for that. So now I'm going to choose A as a root actually. So now what I'm going to do is that I'm going to find the pre-order walk. So I'm going to do starting from A, then I will go to B, then I will go to C, then I will go to H, then I will go to D, then I will go to E, and I will go to G. But what is my original thing? I am starting from A, then I have to get back to my A. So what I will do is, so I will simply do like this. So now you can see very well, I am finding a path actually. So where I am starting here, and I can see that I ensure that there are no what we say cycles are formed, and I am getting back to my original. So this approximation algorithm is called the twice the path algorithm. So you can see another examples also. So this is a graph and this is a MST. So what I'm going to do is I'm going to start from A, and I'm trying to visit all cities. So whenever I am repeating, that means I will try to remove that, because the condition of the problem is that I should visit city only once, and I will simply visit all the cities, and if I have to come back to my original thing, means I will try to add a path, and then I will get back into this sort of thing. In other words, the principle is very simple. So try to convert a problem into some other problem and try to find a solution, and then try to reimburse the original constraints. Okay, so this is how it works. Heuristics normally works, but if you say that fine, will it work for all the cases, means no, there are certain circumstances where the heuristics will not work. So if the heuristics is not working, means fine. So we have to find some other alternative, right? Fine. Next, I will take one more difficult problem called vertex cover problem. We will try to see what is the sort of heuristics that we can do as per that. Again, as I said earlier, for smaller instances, it is very easy, but for larger instances, these things are very difficult. So the problem is I'm given a undirected graph, and then I have to find the vertex cover with the minimum size. Fine. You take this particular undirected graph actually. So cover means, say for example, if I make a node as a cover means, then all the edges are covered. For example, if I make one as the cover means, it covers the edge, let us say 1 to 4 and 1 to 2. This is what the cover means. So what is the uh, uh, arbitrary answer for this? If I make all the nodes as the cover, then the problem is solved. So, but the issue is, what is the size of this means? The size is going to be 6. So the number of nodes are going to be 6. So that means this is not an optimal solution. So vertex cover means I have to find the minimum nodes that can be used as a cover. So that means I have to find the minimum number of nodes only. So in this case only, these sort of things are coming into picture. For example, if you take this particular graph, the minimum vertex cover is empty. So if you take the minimum cover of this means, you can see very well 3 is a better cover, because if I take 3 as a cover, it covers 1 to 3, 0 to 3 as well as 2 to 3, right? But on the other hand, if I take 0 as the cover means, what will happen? 1 to 3 is not covered, as well as 2 to 3 is not covered. And if I take this particular thing, if I take 4 and 2 as the cover means, what will happen is that 1 to 4 is covered, 3 to 4 is covered, then 0 to 2 is also covered. So in other words, the minimum vertex cover is going to be 4 comma 2, or it's going to be 4 comma 0. Fine students, you may think what sort of funny problem this is. Fine, this problem is very helpful, for example, to position hospitals in a city. So that means, where can I put a hospital in a node such that all the edges will be covered? So this is a very useful problem in various domains. And similarly, in computational geometry, you have a problem called gallery problem. Imagine that I am going to put a watchman over here. So if I put a watchman over here means, so this fellow can see all the nodes actually. But if I put a watchman in node 1 means, he can't be able to see this sort of nodes 2 as well as 0. In other words, only one watchman is enough, and this is what we call as the gallery theorem. This is the beauty of algorithms. The problem may look very simple, but in reality, we can cast this problem into number of applications. This is where what you say the NP completeness is coming. Suppose if one brilliant fellow gives a solution for the vertex cover means, suddenly the gallery problem will be solved. In other words, in one stroke, many problems will be solved actually because of one this particular solution, right? So this is the beauty of these sort of problems. So what I will do is, I will try to see how to solve this particular problem for a smaller instance. The heuristic is something like this. What is the criteria? The visibility is the criteria. So that means what I will try to do is that I will take one edge. Edge has got two nodes actually. So I will choose either U or V as the cover. So initially, the cover will start with null actually. Then I will take each and every edge of the thing, and I will try to include either U or V, because of the constraint that that cover will cover all the edges. So I will try to cover either one node or the other node. I will keep on doing that, and if the nodes cover the edges means, I will try to remove that, and then I will repeat until all the results are obtained. So this is what we are going to do. So you take this particular example. So the problem given to me is very simple, to find the minimum what is a vertex cover. So what I will try to do is that I will take one arbitrary edge. For example, I am taking BC as the arbitrary edge. Means what I will do is I will try to cover either B, or I will try to cover either C. So if I cover B, means what will happen is that A is also covered because there is a edge A to B. And if I cover C, then automatically what happens is C to F is also what is a covered. And if I take B, then B to D is also covered. So what I will try to do is that I will try to cover what is a B as well as C. So this edge is taken care of, and this edge is taken care of, and this edge is also is also taken care of. But what is the only one edge that is not covered? This D to E is not covered. Please note, D to E is not covered. So that means I have to cover either D, or I have to cover E. So that means you can see that my solution is going to be BCD, or BCE is going to be my solution for this particular problem. So what about the guarantee? So guarantee is very simple. Every edge is seen twice actually. So that means it should be twice of your MST. MST is nothing but your optimal, means the efficiency or the performance guarantee is going to be what is a maximum limit is 2 multiplied by your opt. This is a performance guarantee. In other words, I can give an approximation algorithm, and that approximation algorithm is nothing but the greedy algorithm. So greedy heuristic. So what I will try to do is that, like a greedy man, what I will try to do is that I will try to take every edge, and then I will try to cover either U or V, and then I repeat this for your entire exam. Okay, so this is the approximation algorithm, and this is the efficiency of this particular algorithm. Then we will see one more problem called a set cover problem. Set cover problem is also a beautiful problem which has got what to say, plenty of applications. So I will start with a description of this problem. So let us assume that I have three different sets, S1, S2, S3, and let us say the elements of set 1 is 413, and the elements of set 2 is 2 comma 5, and the elements of S3 is going to be 1432, and every set is associated with a cost solution. And the set cover problem is very simple. If I uh, combine the sets, that is S1, S2, S3, I should get a universal set, that is nothing but 1, 2, 3, 4, 5. So that means the logic is very simple now. I have to find the minimum number of sets that are available in order to get my universal set. So you can see very well, to get 1, 2, 3, 4, 5, I can combine what you say, this S1 as well as S2. I can combine. If I combine S1 and S2, what I will get? I will get 1, 2, 3, 4, 5, which is equal to my universal set. Or I can combine S2 and S3, that is 1, 2, 3, 4, 5, and I can get my universal set. Two possible combinations are possible. So if I combine S1 and S2, what is the cost? It is 5 plus 10, 15 is the cost. But on the other hand, if I combine S2 and S3, you can see very well it is nothing but 10 plus 3, that is going to be 13 only. So that means the minimum cost is better. Therefore, the better solution is S2 and S3. So the answer for this problem is what is a combining S2 and S3. So You may again think why this silly problem. In fact, viruses are being obtained or found out by computer virus scan program using set cover problems. Let us assume that there are 100 virus which are displaying a property of 1,000 properties means. So you have lots of properties means. So the question is how you will cover such a property so that using the minimum string matching, you can remove those viruses by normal string. In other words, if two viruses display maximum 1,000 properties means, then we can attack only those two viruses, not remaining things. So this is a real advantage of the set cover problem. Similarly, let us assume that you have one doctor who can handle cardiology problem, nephrology problem, and lung related problems. Another doctor will bother only about cardiology problems. Another doctor bothers only about the nephrology problem. Means which doctor is better? The doctor one is better, even though this example is very hypothetical, because he covers more number of diseases. So this is a set cover problem. Why this problem is so difficult means, fine, for some smaller instances like this things can be easily solved, but when the number of elements becomes larger and larger, millions, billions, suddenly this problem becomes very big. So in this case only we require some sort of a methodology to start with, and that methodology is what we are going to bother about these sort of things. Fine, what we are going to do is we are going to design some sort of a heuristic, some sort of a thumb rule. For example, I will start with iteration 1. So in iteration 1, what I'm going to do is that I'm going to include the sets into my solutions, right? Fine. So first set I'm taking. So what are the elements of the set? It is nothing but 413. So 413 is available in what is a universal set. 413 is available. And what is the cost of this particular set? It is going to be 5. So what I can do is that I can take the ratio of this. So that means I will take the ratio of cost divided by how many elements are there. Means it is going to be 5 by 3. And what about the second set? Second set cost is 10, and how many elements are there? Only two elements are there. It is going to be 10 by 2. And third set, if I take, it is going to be 3 by 4. So that means which is having the minimum value. Minimum value is what is a 3 by 4. Therefore, I will take the method of what is a adding S3 into the solution. Now I get a clue of how to solve the problem. In other words, the clue is very simple. I have to take the ratio of the cost divided by how many elements would be covered. So if I take that, and the minimum value is what I should opt for. So now what is happened is that now S3 will go inside. So if now F3 goes inside means it has got only 4 elements, 1, 4, 3, 2. So that means we don't have what is the other element of 5. So that means now I have to add one more set into that. Then I have to see what exactly it is. So now if I take this particular thing means, again I have only two choices, that is S1 or S2. S1 unfortunately do not have the element of 5. So that means you can see very well it is going to be 5 divided by 0, but whereas for this set 5 is there, so it is going to be 10 divided by 1. 5 divided by 0 is what is a indeterminate. Therefore, I will pick up this one, so that means I will try to add S2. So now I have what you say the idea of what to do, and in my book I have given the proof for this. Proof is this is coming with a performance guarantee of log n by opt. So this is the performance of that, and this is the algorithm where we can see that this is the criteria we are using for our thumb rule. Therefore, this is going to be a heuristic algorithm. Will it work always? Means fine. Heuristics by definition will not work always. There are many instances where this sort of what you say algorithm may fail also for some instances, but in general we can say that the heuristics really works. Okay, so this is the approximation algorithm for this sort of problem. Similarly, you can define what is a greedy algorithm for knapsack problem also. So you know very well knapsack problem is very fantastic problem. You have a very great knapsack or a bag, then you have lots of items. Every item has got what is a some sort of a profit as well as weight. So the question is you have to dump too many items into that so that your weight criteria of your knapsack is not violated, as well as what is a you will get the maximum profit. There are two types of problems available for knapsack. One is called continuous knapsack problem, where you can have the fractions of the items, and you have something like 0 bar 1 knapsack problem, where you can't allow fractions. For example, let us say if a thief is entering into your house has got some, let us say, video recorder, it has got TV, etc. Means he can't take partial TV, right? Either he has to take the entire TV or he has to leave that particular item. But if your thief is going to thief something about rice or sugar, means fine, he can take the whole lot of what is a rice with some fraction of sugar also. This is a continuous kind of thing. So these problems haunt the researchers for many years because they are not able to come up with some sort of a solution. A sort of solution for fractional problems is again based on the ratio of your profit as well as weight. And for this particular three items, the knapsack capacity of 20, given profits 25, 24, 15, and weights like 18, 15, 20 to 10, what you can do is one heuristic is you can go for the ratio of the profit as well as the weight, and you can fill it up with your maximum value. So if you go for the maximum value, means you can see that one second item is getting filled up, and rest of the things you can fill with remaining algorithms, and this is what the algorithm you have, and this is what you will get answer for that. This is the knapsack problems. One point of research is that people are trying these sort of problems using linear programming also. If you study the linear programming, you have problems like maximization, minimization, etc. You have linear programming where the constraints can be expressed as what you say some sort of a linear equations, and you can solve it by the simplex method, and we can find solutions for that. So many solutions are there for this sort of problems, where you have some maximization or minimization of some objective function subjected to constraints like this. When these constraints are formulated as a equation of a linear equation, this becomes a linear programming. So people try to solve these sort of vertex problem using this sort of linear programming also. For example, let us say if I say a vertex is part of the cover, means it is going to be 1. If it is not going to be the part of that, means it is going to be 0. So that means for every edge you have one vertex that is covered. So that means if you take the two nodes of an edge, means the sum is going to be greater than or equal to 1. So that means I have an edge, this is covered, therefore this is 1 plus 0, it's 1. Sometimes this is 1, this is also 1, it's going to be 2. But I can't have 0 for this, right? So that means I can formulate this as a linear programming and I can solve this. And whenever you have some difficult problems like 1 bar 0 bar 1 knapsack or something, it becomes something like I should not have value of fraction for this. In that case it is called the fractional problem. In that case it is called integer programming, where what I will try to do is that I will try to find the continuous value, and if it is greater than zero point 0.5, then I will try to add that, otherwise I will not add that at all, right? So this is the kind of solutions I can have, and people are solving hard problems by means of this sort of linear programming also. There is one greatest advantage of linear programming is that this linear programming always gives optimal values. There is a guarantee for that. In fact, you have a theorem that is no matter what design strategies are used, actually the strategy that involves a linear programming always gives the best results. There is a theorem for that, and if you solve these sort of problem using this sort of things, then definitely this will be what we say a closer optimal solution also. This is also one way of solving these sort of problems. And another way of dealing this sort of hard problem is very simple. That is, you remember my earlier talk, I said these problems are very easy for smaller instances, but these problems are very difficult for larger instances. Means that means we are trying to attack the size. So that means we are trying to reduce the what is say values of the profit and all, and then we try to solve using some simple technique like dynamic programming. These sort of problems are called pseudo polynomial algorithms. You know what is meant by pseudo? Pseudo means false. So that means you are designing some sort of pseudo polynomial algorithm which works fantastic for what is a smaller instances, but allows it flaps for what is a larger instances. For example, you take this particular knapsack problem. I have a value, and I have weight actually. So what I will do is I will try to scale down by means of an adjustment factor, and if I take the maximum value is 16 here, means so 16 multiplied by what is a zero point 0.5, half the factor, and divided by 4, that is number of instances 4, means it is giving a value of 2. So now what I will do is I will try to scale down this value by this particular factor. So 12 divided by 2 is 6. 16 divided by 2 is 8, and 4 divided by 2 is 2, and 8 divided by 2 is going to be 2. In other words, suddenly what is happening is that my values are coming down to what is a lower value. Now this is what I said, the values are scaled down to a smaller one, and when the values scale down, potentially this becomes a easy problem. I say potentially, right? So that means there is a possibility that this may be a lesser instance which I can solve using dynamic programming, because in dynamic programming you have algorithm to solve these sort of problems. But again, please remember, we are not working on the original values. Therefore, the polynomial algorithm which we have is a pseudo polynomial algorithm. In short, you can have lots of what we say performance guarantees, and you can have these sort of problems as per that. So in other words, I can say approximation algorithm is a superb research area where you can try to handle these problems, and you can devise some beautiful heuristics. You can approach greedy based methods, you can approach linear programming methods, or you can approach these sort of dynamic programming pseudo polynomial algorithms to handle these sort of things, right? So it's a perfect area for research where you can attempt to solve these sort of problems, right? Fine. Now we will move on to the other category. So now what we have seen earlier is an approximation, where we try to devise some sort of an algorithm so that it will not give you the exact result, but something closer to that. That is what we have seen. Now we change the other route. We try to solve that using the randomized algorithm. What is a randomness? Randomness is nothing but your system whose behavior is not following any deterministic or predictable pattern. Imagine like this. Uh, for example, you are having a company. Let us assume like that. So you are producing some 100 transistors. So you are the quality control check engineer also. So what you will do? 100 transistors. So you will take each and every transistor. You will try to tune it on. You will check if it is perfect. You will say it's a good quality transistor. Otherwise, it is not. You can do all the things. Everything looks very perfect. Suddenly, you are producing 10,000 transistors. Means what you will do? You alone can't do the job. You will try to employ some 5 people for that. So that means you try to improve the quality by employing more persons. Suddenly, the number of transistors becomes 1 billion. What you will do? Fine, things are becoming very difficult. You can't control, check each and everything. What you will do is randomly you will pick something, and then you will try to apply the quality control program. You may ask a question, sir, there are certain possibilities where all good transistors may come together. Means, yes, that possibility is there, but there are no other ways to do that. So, incidentally, the transistors that you are choosing are all of good quality, therefore, you can give a good certificate saying that all transistors are good. There is also another possibility that you take some transistors which may be all what is a flawed transistors also. In other words, randomization means it's based on probability. In other words, these are called the probabilistic algorithm, where the main core of the element is some sort of a randomness. In other words, it is not like your deterministic algorithm where you get all the results on given a particular input. In probability randomistic algorithm, actually, the output will change also because it is not dependent only on the input actually, but it is also based on the randomness that is built into the process. Therefore, based on the randomness, things will really change. So this is a kind of algorithm which we are going to do, and randomness you can encounter in almost all gambling, puzzles, decision making process, the heuristics, etc. And lots of advantage is there. It's very simple algorithm based on few probability, randomness. It's very efficient. Computational complexity is amazing because people don't know how to explain this methodology, but nevertheless, probabilistic things seems to really work actually, and disadvantage is that reliability. Like I said, you take some 5 transistors randomly, 5 may be very good, so you may give a fantastic certificate, but which may turn out to be a what is a horrible thing to do also. So reliability is a question, and the quality is dependent on the randomness. Randomness dependent on the random number, and you know very well, given the precise memory and processor we have, we can't define a random number perfectly. So all we are trying to do is some sort of a pseudo random number which are closer to random number. In other words, the better random number we are generating, the quality of the program is going to be better. Okay, so this is what it is. There are two types of probabilistic algorithms we have. One is called the Las Vegas algorithm, and another is called Monte Carlo algorithms. Las Vegas algorithm was proposed by Laszlo Babai. So he is a Hungarian mathematician. So he has defined the Las Vegas probabilistic algorithms. It's probably very fast, and the results are always right actually. Okay. Either you will get results or your program will run infinitely and you will not get any results at all. But you will not get any false answer because of Las Vegas. Okay, this is a very important point to remember. So that means if you try to define an algorithm, means there is no guarantee on the termination like your deterministic algorithm, because these are dependent on some random choices. Normally they will terminate. Sometimes it may not terminate also. Las Vegas algorithm property is that if it really terminates, it will always give you the correct answer. Otherwise, it will not uh, give any answer. It will go on in an infinite loop. So normally random quicksort is being solved by means of these particular algorithms. So it's a very popularized modified version of quicksort. We will explain a little bit of time. So I will try to define Monte Carlo algorithms also, which are what to say the other side. You can compare this with your earlier thing. Earlier program is always right, but whereas here it is mostly or probably right. So that means every output is associated with a probability, and if the probability is more, then it is right. And if the circumstances are like that, means it is also maybe wrong also. In other words, these things will have one guaranteed output. True means it is always true, like our corona test which we are saying. So if it says that this fellow has got corona, means 100% he is having corona. But if it says that this fellow is not having corona, means it is coming with some sort of a doubtness or probability that this fellow may have corona or may not have. In other words, you have some fantastic primality testing algorithms where if you have to check whether a number is a prime number or not, means if it says it is not prime, it is 100% that it is not a prime. But on the other hand, if it says that this is a prime number, fine, there is some sort of a doubt in that it may be turn out to be a false thing also, because it is associated with a probability. Probabilistic algorithm are one of the finest gems of algorithm theory, so which has solved lots of problems. In fact, the primality testing was considered to be NP hard problem even 20 years back actually, but now you have fantastic solutions available using the randomized algorithm. Now people say with confidence that primality testing is not an NP hard problem, but it is a sort of easy algorithm. So this is what people say as part of that. Fine, we will see what are the design principles that are involved. So I will take one principle called what we say random sampling or ordering. So that means what I will do is I will take one input order and then I will really shuffle it. This is what I call as the randomization. Once I shuffle that, then I will try to design a sort of randomized algorithm similar to your deterministic algorithm, and then I will try to solve that. Okay, this is what one design strategy, and I'm going to explain this with respect to a problem called what is a hiring problem. Hiring problem, let us define like this. Let us assume that in your company, you are the boss, you are the owner, you want to appoint a secretary. So you are asking the employment agency to send some 100 people. Let us assume like that. Fine. So what you do, first people you are calling in for your secretary, and then you try to assess the talent of that particular category, and talent you call it as a rank, and then you say that rank is one, and then you are hiring that particular person. Please listen. First fellow comes, he seems to be a better secretary because you haven't seen anybody before that, so you are trying to hire that particular person. Second fellow comes, then you are trying to compare the quality of your second candidate with the first candidate. If the second candidate is having a better quality than your what is a first secretary, means then you are hiring the second fellow and then you are trying to fire the first fellow. So if I keep on doing like that, fine, what happens is that if I interview n candidates means I have to assign a cost for hiring and I have to assign a cost for firing. So that means you can see very well, this is definitely a order of M and N, where nothing but hiring as well as firing as part of this particular strategy. So this is what you say the deterministic algorithm is. So what is the problem with this? Problem with this is very simple. This number of employees may become 1,000, number of employees become 10,000. What is the worst case of that? 10,000th candidate may be a better candidate. In that case, actually, what you will do is you will hire all previous people and then you will try to fire them. So this is the real problem with this sort of deterministic algorithm. Fine, can I go by probability as a means? Yes, we can do. We can employ the principle of shuffling. So what I will try to do is that I will take 10,000 people. I will try to shuffle them. That's all. I will try to shuffle them, and then I will try to what you say apply the same deterministic algorithm, and then I will try to assess the performance. Right. So you can see very well the difference between this randomized algorithm and your previous algorithm is that the first step where I am trying to permutate these sort of things. By shuffling, what will happen is that the 10,000th candidate may become a 100th candidate also. There is a possibility. If it happens, if it really happens, means at the 100th step, I will find a better candidate. This is a logic behind this sort of thing. So, in other words, I can prove that this algorithm is better by introducing the concepts of probability. One concept is called what is the indicator random variable. Indicator random variable says it's going to be 1 if the event A occurs, it is going to be 0 if it doesn't occur at all. So what is the event in our case? In our event, it is nothing but the hiring of candidate. 1 it is going to be hired and 0 it is not hired. In other words, this becomes a what is a random variable. So now you have a random variable associated with the first candidate, second candidate, third candidate, fourth candidate, up to nth candidate. And what is the probability of fellow is selected? It is equally probable because all candidates have got possibility of getting either hired or fired. In other words, it is going to be equally likely. So that means you can see very well it's going to be the expectation actually. Every person has got probability of getting selected or not selected. So that means equally likely. That means it's going to be 1 by I. So which is nothing but log n. So how I will give a justification for my probabilistic algorithm? I will say that the time complexity analysis for the deterministic algorithm is what is a order of n. But whereas in probability, it is going to be order of log n. So that means suddenly you see that this algorithm becomes a better algorithm. Okay. So this is how you will give you a proof, and uh, using this you can solve the hiring problem very nicely. In fact, the hiring problem has become a very classic problem to explain the superiority of the probabilistic algorithms. Second case is called witness. So witness is something like this. Whenever I say that all the students of this class are intelligent, means if I show one instance where the student of that particular class is not intelligent, means then all students of this class are intelligent is nullified. That is called the concept of witness. So I take some witness and I try to prove that this concept is right. And if I able to prove one witness that this is not the case, then this becomes a counter example. Primality testing is a very fantastic problem. It is considered to be NP hard for a very longer time. You know what is a prime number is? Given a number, if it is divisible by 1 and by the same number, it is called a prime number. For example, 13 is a prime number, 17 is a prime number. What is the difficulty with this problem means, for smaller number it is so easy. But if I give you a bigger number like 1, 2, 7, 5, 6, 7, 9, 8, 9, 9, means is it a prime or not, means this is where problem comes. Either you have to start taking from 1, 2, 3 onwards till that number to check whether it is divisible by any other number, or you can go from root 2 to root n. No matter whatever it is, for a very large number, this process takes lots of. This is the problem of primality testing numbers, and people have struggled with this problem for many centuries. And this is what is a Fermat. So Fermat gave a theorem called the Fermat theorem, which he says that if this condition holds, then it is a prime number. So that means x is going to be a number arbitrarily you will be choosing, and n is nothing but the number you want to prove whether it is prime or not. If this is the case, then you will say that it is a prime number or not. So that means what you will do is very simple. You will try to take some witnesses. Witnesses means I will try to randomly select some numbers, let us say 5, 7, 15, 18 and all. Then I will try to apply that into this particular formula. And if I find one, means I will declare that according to these witnesses, this number is a prime number. So that is what I will try to do. And if even if one witness says that this condition doesn't hold good, means then it is not a prime number, but it is a composite number, right? So you may ask a question like that. Fine. If I have to try all the numbers, is it not equal to a deterministic algorithm? Means yes, it is. So for example, let us say polling analysis is being done. Some psephology takes some samples of 10,000, conducts some mini election, and then argues, analyzes that. If the sample size of the survey is equal to the sample size of your entire city, means it becomes a general election. In that case, randomized algorithm don't help at all. In that case, deterministic algorithm will really help. But when the survey will hold good, when the survey hold good, when the samples are representative, which is a indicative of your general population, in that case it really works. So algorithms have been tried based on this concept of fitness. So that means you will choose different values of a, but you will take the number n, and then you will see whether that congruency to one holds really good or not. If it holds good, means then you will come to a conclusion that it is a primality number, otherwise it is not. And what is the order? It is nothing but order of log n steps. So that means this is a better algorithm compared to your traditional, what they say, order of n, where n is nothing but the size of your particular digit. Okay, so this is the advantage of this particular thing. Fingerprint is another strategy. Fingerprint is something like a hash function kind of things. So what I will try to do is that I will try to take a bigger number. I will try to apply some sort of a hash function, and then I will try to find a fingerprint kind of things, and then I will try to use these sort of things. Assume like this. I have two strings. Let us say each string consists of some 1 billion bits actually. So A is a 1 billion bits, B is a another number with 1 billion bits. Somebody is asking me whether A and B are same or not. Means what is the brutal algorithm is going to be? I will compare each and every bit. I will go up to 1 billion to say that whether the things are similar or not. In fact, the virus checking programs are like that only. Every virus is nothing but a set of strings actually. So that means I have 1,000 possibilities of virus, means I have to keep on checking. If the number of strings becomes very, very larger, then things are becoming very difficult. In that case, I can go for a randomized algorithm. What I will do is, I will not go one by one, but arbitrarily, randomly, I will pick up some bits actually. I will take first bit, fourth bit, ninth bit, 11th bit, 27th bit, and all. If necessary, I will try to apply some sort of a hash function over that. I will have a very smaller number. That smaller number is what I am going to call the fingerprint of your my largest. Suddenly, my problem of comparing two strings becomes comparing two fingerprints. Suddenly, what is happening is that I am taking the message A and I am finding the fingerprint of M, and I am finding the fingerprint of message B into fingerprint N. So suddenly the problem becomes comparing two fingerprints. If fingerprints are same, then the strings are same. If not same, then it is going to be false. This is what the randomized algorithm is. What is the worst case? Worst case is, for example, if I choose 1, 3, 7, 9, 11 kind of things, there may be some possibility that your instances are such that it may be true, but there are many bits which are available may not be actually so. That possibility is always there. But nevertheless, what is our original contention? The problem of comparing 1 billion bit is very difficult. So something is better than nothing. Therefore, instead of comparing 10,000, I will take a risk by taking what is a fewer bits. That fewer bits is nothing but the bit. If I want to increase the reliability, instead of choosing some 10 instances, I can choose 100. I can choose 200. I can choose 300. If I increase the size of that particular instance, then the reliability of the program is becoming larger. So in other words, I will try to increase the witness to improve the probability. Will I increase the instances to witness to billion? Means no. If I make the witness as 1 billion, then it becomes a deterministic algorithm. So I will not go for that, but I will go for a reasonable witness and I will choose this sort of things. Suppose if the fifth bit is differing, therefore both the strings are not equal, means it is associated with a probability of 100%. This is nothing but what is a Monte Carlo algorithm. Therefore, if it says that strings are not same, it is not same at all. These algorithms play a very beautiful role in computer science. It is useful in virus scanning, softwares, etc., where the quality time is consumed like anything, so program seems to execute faster. Okay, so this is the advantage of this, and the complexity is nothing but order of log n. Of course, this is pseudo polynomial, but nevertheless randomized algorithms. And randomized quicksort is also one example. You can go through that. You know quicksort very well. You choose a pivotal element, so you have lots of algorithms available for that. So now what are you will do is in randomized algorithm, I will simply push away those things, but instead I will choose a pivot element randomly. That's all. I will choose randomly, and this becomes a randomized algorithm for quicksort. Now you can see very well, I am not using any algorithms for finding the pivotal element. Just like that, randomly I will do that, and I will start comparing that by means of my indicator variable. So now what is the indicator variable for that? For pivotal, it's nothing but comparisons. So I will try to define a random variable for these comparisons. So I will try to compare two elements. Two elements will never be compared, or possibility of one element becomes the pivotal element. And if I find out all the things and I see that, it's going to be what is a order of n log. Students, this is very beautiful because what you say, this is what you will get more or less in your deterministic algorithms also. But the major advantage is that, fine, you have a situation where you don't apply any algorithm for finding the pivot. So how can it be justified? For example, if I have some very smaller numbers, say for example 1000 or 10,000, I may not perhaps not require randomized algorithms at all. In that case, I can straight away go for deterministic algorithms. Approximation algorithm, randomized algorithm are special cases where the problem is so tough. If you have 1 billion elements for quick sort means, in that case, you can go for the randomized algorithm, right? So this is the logic behind that. So I summarize that you have what you say randomized primality testing algorithms are available now, so which are making large impacts. So you have beautiful randomization algorithms available for many number of problems like string and all. So these are some of the books you can refer. I have given one chapter for that. You can also refer Corman to get some more ideas. And as I said earlier, this topic is meant for researchers. If any faculty members are interested in doing research in approximation algorithm or probabilistic algorithm means, you are welcome to do research, because there is a lot of potentials are there in this, especially the linear programming. So due to time constraints, and since I don't know the background of the students, I haven't taught much about linear programming. But linear programming is one such thing is available to implement all these sort of problems. Students, I tell you one thing, in your talent kit, approximation algorithm and randomization algorithms are very important, because more or less you people are going to work in industries on some problems. Sometimes the problems may become very complicated. You spend your time, let us say 6 months, 7 months, and if you say problem is so difficult, can't be solved, the manager perhaps may sack you. But on the other hand, if you say that this problem is not solvable by me, but also by other people, and this is a reason for why this problem is so difficult, then you will get a promotion also. Because instead of dealing with a difficult problem for 3 years, 4 years, and then saying that this problem is unsolvable, so with just paper and pencil, if you give you a proof that this problem is not solvable, then it becomes a classic case of what is a geniusness in mathematics, right? So with this thing, I have completed my portion. So if you have any doubts, you can please ask me. I'm very happy to answer if it is coming under my purview of research. Thank you.
Thank you, sir.
Yes, sir. Any questions, sir?
Yeah, sir, till now, even I haven't received any question. Participants, if there are any question, if you want to ask any question to sir, maybe you can type in the chat box here. Or if somebody wants to speak, maybe they can raise their hand. Okay. Rima ma'am, Professor Rima Threja, would you like to speak something, ma'am? Ma'am, could you please unmute yourself?
Yes, in fact, I
Yeah.
was trying to do that.
Yeah.
Uh, yes, thank you, Dr. Sridhar. This was a very knowledgeable session, and we all were benefited by your uh, the depth and the knowledge that you have. I have gone through your books, and they're very, very easy to read. And I really appreciate your hard work. Like,
Thank
I'm
you.
not teaching algorithms, but it has helped me a lot to understand the concepts, and I'm sure my students also like that book. So we were very much enthusiastic to have a talk with you. In fact, we wanted that it should go for at least 2 hours, but because of some prior engagement, it couldn't be possible. And I really thank you, and we are grateful. I'm grateful on behalf of my college to spare out your time and share your knowledge with us. Thank you
Thank,
so much,
thank you,
Dr.
madam. Thanks a lot, actually. So it's a great privilege to interact with you. So, as you said, I would have spent more time actually. So, I'm very happy to be part of this discussion and to share the knowledge with you. So, if you have any doubts or any clarifications, even for your students, you can always contact me, madam. I will try my level best to help all of you. It's a
Thank you
great
so much, sir. That is so nice of you.
it's a great privilege to be part of this webinar, madam. In fact, I'm very honored by your kind words, actually. Thank you.
Yes, sir. Thank you so much.
Thank you, madam.
uh, and participants, so I guess you'll be receiving your certificate of participation, a CE certificate, I think, within a week, Rima ma'am. Like,
Yes, sir. Within a week, we'll send it through email.
okay, so ma'am, what I'm doing is I'll put in um, uh, an email ID here. Actually, our marketing department email ID, and if the participants have any query about the certificate, they can always write to me, and I can forward that query to you. Would that be fine?
Yes, sir. Thank you so much. Our
Okay, I'm
students will
just
also be coordinating with the participants to make sure that everybody gets a certificate of participation.
just in case if somebody doesn't receive it, I'm just so here
Mansi Jain, can
I've
you
shared
hear me?
I've shared my email ID. If there is any other email ID you want to share, you can.
Yes, Mansi Jain. Please share your email ID in the chat box so that participants can get in touch with you.
Nidhi Garg is asking for PPT. Nidhi Garg, ma'am, we'll be uploading this on our YouTube channel, so we can share the link with all the participants of this video, this webinar recording. Yeah, thank you.
So I'll just put. I got her email ID. I'll just put in the chat box
Sure,
so that
sure, sure,
everybody can
sure,
share. Yeah,
sure.
I'll just do that.
Dr. Sridhar, there's one question
Sure.
from Miss Shweta Sharma.
Okay.
How the algorithms can be applied in medical domain?
Yeah, algorithms are same. You can apply algorithm irrespective to any domains actually. But the only caution you should take is that uh, in medical you are dealing with lives actually. So the quality of the program is very important. For example, if you are applying some classification program, let us say to some general plants or flowers, so the sensitivity or specificity of that is of no matter of concern. But on the other hand, if you apply the same algorithm to a medical domain, something like a cancer, sensitivity and specificity are very, very important, because even a very small mistakes there can cost the human life. So that is the reason why we are going for some cost sensitive classifier for that. So that is the basic difference between the medical domain and other domains. Algorithms are algorithms that can be applied to different domains, but there are certain criteria in which you should not have any flaw at all. For example, you are designing a algorithm which has got some reliability issues. For example, randomized algorithms, right? So take this example itself. If you apply this to some what you say some industrial problem, means it's fine. But can you apply that to a medical domain? For example, can you arbitrarily choose a gene for comparison? Means fine, it cost is not so easy. It is coming with some risk also. So you should be very cautious about application of these algorithms. So that is the question of research actually, right? So that means you do lots of analysis, statistical analysis, and only if you are very optimistic about what you say, taking care of this sort of abnormal cost, then you can go for it. Otherwise, better try to avoid that. Normally, approximation algorithm we don't try with medical domain. Yes, sir.
Thank you, sir. Miss
Is it answer for our question actually?
Sir, I hope Miss Shweta, yes, she has replied. Thank you, sir.
Yes,
So I think
yes. Sir, another student raised a hand. Suman, Meena.
just hold on. I'll unmute the. Uh,
One
Unmuted the.
student raised.
Uh,
Suman,
please,
Meena.
yeah, please go ahead, Suman Mina. You can unmute yourself and ask the question. Sir, I guess there is some connectivity issue.
Okay.
Sir, should we conclude this session then?
Yes, sir. Yes, sir.
Okay, sir, and thanks a lot, sir. On behalf of Oxford University Press, I thank you. I
Thank
thank
you,
you
sir.
for
Thank you very
taking
much.
this session, and also I thank the participants for their presence, and of course I thank Shyama Prasad Mukherjee College for Women for.
Thank you very much, sir. Yeah.
Thank you, sir. Thank you
Okay,
very much.
thank you everyone. Bye. Please take good care of yourself.
Thank you, sir.
Thank you.